Okay, in last lecture we have discussed about uh, that is the sorting basics and the issues related to the sorting algorithms, if you see there. So those issues we have discussed regarding the where the input sequence will be stored or where the output sequence will be stored, if you see there. And then we have discussed about the sorting uh, algorithm can be comparison based or the non-comparison based, if you see there. And then we have discussed about the lower bound on any comparison based sorting algorithm. Okay, in terms of the asymptotic notation, its lower bound is theta of n log n. That is also discussed. After that we have discussed about the uh, that is the sorting that is the parallel compare exchange operation or the sorting with one element per processor or one element per processing element we have discussed. Okay, and after that we have seen the uh, that is using the parallel compare split operation or the more than one element per processing element or the processor. That kind of discussion we have done in last lecture, if you see there. Then moving towards the next topic, that is the sorting networks, if you see there, because in sorting algorithm you are using the compare and exchange operation, if you see there. So this is called as a comparison based algorithm. So in that case, how those parallel sorting networks are designed, if you see there. So it is having the networks of the comparator. Okay, if you see there, and it is specially designed for the sorting operations, if you see there. So what is comparator? You might have doubt in your problem, because sorting network topic is given in your syllabus. Okay, in some books it is taken, in some books it is not taken, but you should know the basics about the sorting networks also. And sometime question may be asked, what is sorting networks and how it is designed for the sorting that is the n number of elements, if you see there. Okay, and especially it is designed for the parallel algorithms, if you see there. So you should know that is the comparator is nothing but the one kind of device and having the two inputs x and y, if you see there, and having two outputs it will produce, that is the x dash and y dash. Okay, and in case there are two types of comparator, that is increasing comparator and the decreasing comparator. If you see there, increasing comparator generally represented using the circle with the plus sign, and decreasing comparator generally represented using the circle with the minus theta, if you see there. And for an increasing comparator, how that x dash output will be produced, x dash equal to min of xy. Xy is nothing but the you can say the inputs to that comparator. So minimum of these two will be considered as x dash, and y dash will be the min of xy again, if you there, and vice versa. And the in case of this comparator, speed of the network is proportional to its depth, if you see there. It depends on the number of elements also, and the number of parallel comparator you can say the uh, added in that particular network, if you see there. So we'll see that kind of diagram also. So sorting network comparators, if you see there, which we discussed just, that is first one is showing the you can say the increasing comparator, and the second one is showing the decreasing comparator. So in case of the first comparator, x, y are the input, x dash, y dash are the outputs produced. In second rightmost figure, it is showing the its notation, that is the increasing comparator is used, represented using the circle with plus sign. Okay, for x dash as well as the y dash, if you see there. In case of the decreasing comparison, that is the change in case of the diagram B only, if you see that. In case of the increasing comparator, you are searching mean of xy. Okay, and in case of the decreasing comparator, you are using the max of xy. Okay, if you see that as an output, that is the x dash and y dash, if you see there. And the notation for the decreasing comparison is just that is the circle with minus sign there, if you see there. And we are getting output as x dash equal to max of xy and y dash equal to min of xy. Okay, in each pair of elements in that particular sequence, if you see that. So this is the schematic representation of comparators. A is the increasing and B is the decreasing comparator. If you see there. So we'll see it in brief because we'll not waste too much time on this particular, but you should have the knowledge of that is the sorting network design, how it is actually designed. If you see that, because this diagram showing the typical sorting network. If you see there, okay, it is having the number of columns of that is the parallel comparators. If you see there, which are in parallel fashion. If you see, and typical sorting network is shown here, and every sorting network is made up of a series of columns. Okay, and each column contains a number of comparators connected in parallel, as discussed. So interconnection network is shown here, and it is having the multiple columns, and each column contains the number of comparators connected in parallel. If you see there, those comparator might be increasing comparator or decreasing comparator. If you see there, and those comparator will have the input wires to accept the inputs. Okay, if you see there, and input will be in the form of the two elements xy. Okay, if you see there, and output will be x dash y dash in dash form that will be produced there. If you see there, if there are n number of elements, if you see, so pair of elements will be considered as x dash y dash. If you see there, that is the xy, that is the 1 2, then so you can see the x1 y1 1 2 x3 y3 3 4 likewise. Similarly, x dash y dash x1 dash y1 dash x2 dash y2 dash. In this way, that is the output will be produced. If you see there, so this is a sorting network shown in this current diagram. Then as you are familiar with the sorting networks now, so there is one sorting technique, Bitonic sort. If you see that, so actually in your syllabus focus is given on the bubble sort, that is the parallel bubble sort. Okay, now and then the cell sort is also given there, and after that that is the focus is on quick sort, and how you can design the parallel quick sort algorithm. Let you see that. So these three algorithms are there, but apart from this one, in brief, Bitonic sort also we will discuss here, because in some books this algorithm is taken. If you see that, that's why we need to discuss it in brief. If you say that, and why this sorting is called as Bitonic sort, because sequence of element in that particular you can say the sort. If you see that, they are either in a you can say the in a particular cyclic sequence order. If you see that, for example, 1 2 3, then again 1 2 3, and followed by 1 2 3, followed by 1 2 3. This is cyclic sequence. Okay, this is also called as the Bitonic sequence. Okay, or it may be increasing decreasing. For example, 1 2 3 4 3 2 1 2 3 4 again 3 2 1. So increasing decreasing, this is also called as the Bitonic sequence. In this way elements are sorted in case of the you can say the Bitonic sort. So we will see that one here. The Bitonic sorting network sorts n elements in theta of log square n time. Okay, so this is the you can say the complexity of the Bitonic sort algorithm. A Bitonic sequence has two tones, that is increasing and decreasing. You should know. That's why it is called the bi. Bi means two. Okay, tonic means two tones, increasing and decreasing. If you see there. Okay, any cyclic rotation of such network is also considered Bitonic. Just I have discussed that is the cyclic network, like 1 2 3 1 2 3 1 2 3. That kind of network can be considered as a cyclic network. So example is shown here, that is the list is shown 1 2 4 7 6 0 is a Bitonic sequence. If you see that, why? Because it is initially increasing in nature and then it is decreasing in nature. 1 2 4 it is increasing, again 7 6 0 decreasing in nature, 2 increasing and decreasing. That's why it is a Bitonic sequence. And second list, if you see there 8 9 2 1 0 4, this is also another Bitonic sequence in current slide, because it is increasing then decreasing. again increasing there. If you see that, that is the it is the repetition of the that is the 0, 4, 8, 9, 2, 1. Okay, in this way. So this is the Bitonic sequence, and this is the cyclic shift of that given here 0, 4, 8, 9, 2, 1. You see that. So in this case, the kernel of the network is the rearrangement of a Bitonic sequence into a sorted sequence. If you see there. So uh, your aim will be there. You have to sort those sequences in a particular sorted order, that is either in ascending order or the descending order. If you see there. Okay, so Bitonic sort works on such type of numbers there. If you see there. So we'll not discuss it in depth, but what are important points in your syllabus we'll discuss regarding a Bitonic sort. So as far as the mapping of Bitonic sort on meshes are concerned, if you see that, in this case, the row in the row major sepal mapping, wires that differ at the ith least significant bit are mapped onto mesh process that are 2 raised to, you can say the, this is the floor of I minus 1 divided by communication links away. So if you see there, wires are nothing but the input wires and the output wires, which we have seen in case of the this sorting networks. If you see that, so it is having the input wires, that is the x1 y1 x2 y2 x3 y3 xn yn likewise. Okay, so they may be represented in the form of the binary numbers also. If you say that 0 0 0 1 likewise. So coupled mapping by ith least significant bit are mapped onto mesh processes that are 2 raised to floor of I minus 1 divided by 2 communication links away. The total amount of communication performed by each process is summation of, if you see there, I ranges from 1 to log n, next summation of j ranges from 1 to I to raised to floor of j minus 1 divided by 2. So it is congruent with 7 root n or theta of root n, if you see there. And the total computation performed by each process is theta of log square n in this case. So the parallel runtime of this kind of Bitonic sort will be Tp equal to theta of log square n, number of comparisons will be required, plus communication cost, that is theta of root n. Okay, so in this way it can represent the parallel runtime. You see that, and again this is not a cost optimal algorithm. If you see that. Okay, so in this case also that is the, in case of the Bitonic sort, you can provide each process a block of n by p elements. If you see that, so number of elements are n, and p indicated the processing elements. If there are 100 elements, 100 divided by a number of processing elements are 10. There, so n by p means 100 by 10 means 10 elements per processors. Okay, will be provided there. If you see there for sorting purpose. Okay, the first step is a local sort of the local block only, and each subsequent compare exchange operation is replaced by a compare split operation. So compare exchange operation we have already discussed, that is the each processor either having the one element per processor or the collection more than one element per processor. So compare split operation is nothing but the more than one element per processor. In our example, we have considered here 10 elements per processor. Means each processor will have the sequence of 10 elements. Okay, or this might be the Bitonic sequence. Okay, either in increasing and then decreasing nature. Okay, if you see that, and we can effectively view the Bitonic network as having 1 plus log p into log p divided by 2 steps, if you see that. So these many steps may be required for the Bitonic sort. So blocks of elements per processor, if you are mapping your Bitonic algorithm with hypercube, if you see that. So in this case, initially the processors sort their n by p elements. We have just discussed that is, each processor will have the n by p elements, or in our example, we will consider 10 elements per processor out of 100 elements. So each processor will have the 10 elements or sequence of 10 elements. So using local sorting method used is merge sort there, if you see there. So initially the processors sort their n by p elements using merge sort in time theta of n by p log n by p, because you know that is the average case time complexity of merge sort, that is theta of n log n. So here value of n is nothing but the per processor, that is n by p. That's why n is replaced by the n by p, theta of n by p log n by p, and then perform the theta of log square p compare split steps. Okay, because here that is the more than one element is there per processor. That is the, if you are considering 100 elements, there will be the 10 sequence of 10 elements per processor. Okay, so it will require the theta of log square p compare split steps, means theta of log square 10 compare split step, if you see there. And the parallel runtime of this formulation will be represented using this particular you can see the equation. TP means parallel runtime. TP equal to theta of n by p log n by p. That is it is required for local sorting using the merge algorithm, plus theta of n by p log square p for comparison. Okay, if you see there, and plus theta of n by p log square p. This is for communication, because each processor is communicating with the its next neighboring processor. That is the processors are arranged in a increasing order of their IDs. If you see there, so they need to communicate and they need to exchange their sequences also in order to sort those sequences in a proper order. That is either in ascending order or descending order. So that kind of example we have seen in last lecture. That is the compare split operation. If you see there, that is the more than one element per processor. If you see there. So in this case, comparing to an optimal sort, the algorithm can efficiently use up to p equal to theta of 2 raised to log n processes there. And the ISO efficiency function due to both communication and extra work is theta of p raised to log p log square p. So you know what is ISO efficiency function, we have discussed in last unit. Okay, so the ISO efficiency function nothing but the you are expressing that is the parallel runtime of your algorithm as a function of its problem size, the number of processing elements, and the total overhead. Okay, if you see there, so you can use or represent this for this current Bitonic sorting algorithm also. That is the IC efficiency function, and that is in terms of the both communication and the extra work. That is the, you know, that is theta of p raised to log p log square p. Is it visible? Hello?
No, sir.
No, sir. Now it is not visible. Okay. Now it is visible, I think.
Yes, sir.
Yes, sir. Yeah. So we have discussed this one, that is the IC efficiency function for the Bitonic sort. Initially, we have computed its parallel runtime as a TP for considering the local sort, then comparison and the communication. Okay, if you see that among the processors. So and then finally we have derived the you can say the IC efficiency function in terms of problem size, or you can say the number of processing elements, and the uh, another one is the overhead function, that is the T0 or W, if you see there. So blocks of elements per processor in case of the as you are mapping this one with the mesh, if you see that is the Bitonic uh, algorithm. Okay, the parallel runtime in this case is given by TP. This is just discussed in previous slide also. Theta of n by p log n by p for local sort, you are performing using the merge sort. You can see there. N by p logs per p comparisons will be there for compare and exchange purpose. Okay, where you can use the split and exchange sort. You can see there plus theta of n by root p number of communication steps required between the processing elements or the processors in order to exchange their sequences. And this formulation can efficiently use up to p equal to theta of log square n processors. If you see that, and the IC efficiency function can be represented as a theta of 2 raised to root p into root p. If you see that, so in this way you can modify your IC efficiency function also. If you see, so if question asked on the Bitonic sort algorithm, you should know what is Bitonic sort algorithm, because question will be there. What is Bitonic sort? Okay, explain Bitonic sort algorithm with suitable example. Okay, if you see there, so you have to give the example. Okay, if you see there, or sometime you need to explain the Bitonic sort considering the its parallel network. Okay, if you see there, how the typical sorting network is designed. One question will be on that also. If you see there, okay, so that kind of questions might be there. Question on, you can, yes, there might be question on this topic. What is Bitonic sort? Okay, so you have to explain with suitable example, and you should know its time complexity also. That is theta of log square n. Then mapping Bitonic sort to meshes, and what will be its parallel runtime, we should know that also. Which one is not cost optimal. Then blocks of elements per processor. Okay, in case of the Bitonic sort also, you can assign n by p elements per processor. Okay, say, and then you can derive the parallel runtime. Okay, considering the local sort time, then comparison, number of comparisons, and the communication, you can say the steps required there. So in terms of local sort, comparisons required, and the number of communication steps, so you can derive the parallel runtime there. That is the TP, and you can show it in terms of the IC efficiency function also. If you see there. Okay, and then in next step you can modify, that is the your IC efficiency function, that is theta of 2 raised to root p into root p. You can see there. So this is all about the Bitonic sort. That is, we have seen the sorting network, and then after that we have seen the Bitonic sort and how you can apply Bitonic sort for the mesh network, that is discussed. You can see there. Then this is last slide regarding the that is the parallel Bitonic sort algorithm. That is the performance of parallel formulation of Bitonic sort for n elements on p processes. So here you are mapping it with different architecture, that is the hypercube, mesh, and ring. So we have discussed about the mesh, so it will be different for the hypercube and ring. In case of the hypercube, maximum number of processes for equal to theta of 1 will be theta of 2 raised to root log n, and corresponding parallel time will be theta of n by 2 raised to root log n into log n, and IC efficiency function can be represented like theta of p raised to log p log square p. And for mesh we have just discussed, that is the maximum number of processes theta of log square n, then corresponding parallel runtime theta of n by log n, and the IC efficiency function theta of 2 raised to root p into root p. And for ring network it will be maximum number of processes for e equal to theta of 1 will be theta of log n, parallel runtime theta of n. IC efficiency function can be represented as theta of 2 raised to p into p. P are nothing but the number of processing element, n that is the number of you can say the elements in that particular sequence. You can see there. So this is about the you can say the comparison of the performance of parallel Bitonic sort, considering the different you can say the network or the architecture. If you see there, that is hypercube, mesh, and ring. Then moving towards our next topic, and this is important compared to the last two topics, that is the sorting network and the Bitonic sort also. If you see there, because bubble sort is given in your syllabus, as well as it is important algorithm as far as your LP1 assignments are concerned. If you see there, okay. So here we will see both, that is the sequential version as well as the parallel, how we can convert sequential version into the that is the parallel version of bubble sort algorithm. Okay, if you see there, so normal sequential bubble sort algorithm cannot be convert you cannot convert it into parallel algorithm, if you see there. But if you consider the sequential odd even bubble sort algorithm, that can be parallelized, if you see there. Okay, or you can convert it into its parallel version, that is possible. But before moving towards its odd even parallel counterpart, okay, we'll see the that is the sequential bubble sort. Okay, this is the normal sequential bubble sort algorithm. Okay, where uh, you are comparing and exchanging the adjacent elements in the sequence to be sorted, if you see that. So it's that is the pseudocode format is given in current slide. Okay, procedure bubble sort, n elements are there for sorting. Okay, means input sequence having the n number of elements, begin for I equal to n minus 1 down to 1 do. So you know that is there are n number of elements, means starting from 0 to n. So you need to move from, I will start from n minus 1 down to 1, and for j it will start from 1 to I, and then you have to continue this particular uh, process, okay, using the particular loop, okay, for loop. And then do, that is the compare exchange aj comma aj plus 1. Okay, if aj is greater than aj plus 1, you need to swap those two elements. Okay, and then next element will be compared, that is aj plus 1 to aj plus 2, and so on, if you see that. And n bubble sort, so this is the we can say the normal or sequential bubble sort algorithm studied. And you know its time complexity also, that is the complexity of bubble sort, which we have seen in last slide, having the theta of n square. And this algorithm, that is bubble sort, is difficult to parallelize since the algorithm has no concurrency. So sometimes question might be there, why you cannot directly uh, convert your normal bubble sort algorithm into its parallel version, if you see that, because it lacks the concurrency, if you see that. That's why instead of this normal bubble sort, you are using the odd even bubble sort, and which you can convert into the parallel bubble sort algorithm. Okay, so that's why we have considered here bubble sort and its variants. Okay, if you see that its variants is nothing but the odd even bubble sort, if you see there. That is also the sequential odd even, and from that sequential odd even bubble sort algorithm, you can convert it into the parallel bubble sort algorithm, if you see there. So this is the sequential odd even bubble sort algorithm is also shown here. Procedure odd even n number of elements, begin for I equal to 1 to n do. Okay, so we'll take that example also. So for in LP1 we already discussed this example, but that was for particular batch only, I think. So we need to discuss it again here. So begin for I equal to 1 to n do. Okay, and begin if I is odd, then okay, because you have, in every step you are dividing your elements into two parts, that is the odd indexed element and the even indexed element. If you see there, if it is starting from 1, so 1 3 5 7 9, these will be the odd indexed elements. Okay, or these are also called as the odd element, if you see there. And those are at place that is just 2 4 6 8 10. So those are the even indexed element, or these are also called as the even element, if you see there. So you have to remember this process there. Begin if I is odd, then I is the index, you should know. Then for j equal to 0 to n by 2 minus 1 do. So why n by 2 minus 1 do here? Because there will be 50% means n by 2 out of n by 2 will be the that is the even index elements, and n by 2 will be the odd index elements there. If you see that, then for j equal to 0 to n by 2 minus 1 do. Okay, compare exchange, that is the a to j plus 1 comma a to j plus 2. That is the this is nothing but the we have considered only the a to j plus 1. These are the odd index elements, if you see there, and you are comparing that odd index element with its right neighbor, that is the even index element in that particular step, if you see there. And if first one is that is odd index is greater than even indexed or neighbor element, then you need to exchange those two elements. Okay, so pair of comparison will be there. If you see that, that is the first will be compared with right element, that is the 2, 3 with the 4, 5 with 6, 7 with 8, and 9 with 10, if you see that. Okay, if they are not in proper sequence, then you need to exchange those two elements. That is the, if at first location 3 is there and at second location 1 is there, in this case you need to swap or exchange their location. 1 and 3 will be there in second step. Okay, this is about the mod step. Then if I is given, then for j equal to 1 to n by 2 minus 1 do compare exchange a to j plus 1. Okay, so alternate steps will be there. That is the first step will be the odd step, and second step will be the even step. Again third step will be the odd step, and fourth step will be the even step, and so on. Okay, so one odd step plus one even step, it will be the one pass of that odd even sort algorithm, if you see that. So in case of the even step, compare exchange a to j comma a to j plus 1. Okay, so in case of the even step, that is the index or the element having the index 2, 4, 6, 8, 10, likewise. Okay, they will be compared with its right neighbor, that is the you can say the uh, 3, 5, 7, 9, 11, in this way. If you say that, if they are not in proper sequence, you need to exchange their position. Okay, if they are already in proper sequence, keep those elements as it is, if you see that. So in this way, odd even transposition of the odd even bubble sort works there. Okay, and for and odd even. So this is the sequential version of the odd even, uh, that is the sort algorithm. If you see there, this is also called odd even transposition sort algorithm, if you see. So this example is given here, which we just discussed. Okay, page 1 odd, page 2 even. Okay, page 1 odd means index 1, 3 having index 1, 2 having 2, 3 having 3, 8 having 4, 5 having 6, and 6 having 7, 4 having 8, and 1 having 9 index, if you see that. Sorry, this is 1 to 8 means 1 will have the index 8 there, as we have started our index from 1. In that case, if you see there, if you are starting your index from 0, so last element will have the index as a 7 in this case. But here we have assumed we have started our index from 1 here. So page 1 odd. Okay, odd element will be compared with the next right neighbor, and if they are not in proper sequence, you need to exchange their location. Okay, and in second step there will be the even page 2. Okay, similarly that is the even element will be compared with its right neighbor, and if they are not in proper sequence, you need to exchange, and so on. In page 3 again odd page will start, page 4 even page 5 odd page 6 even page 7 odd page again, and finally page 8 again even page will be there. Okay, so at the end of page 8 all elements are in sorted order, if you see there. Okay, so total number of passes required here, 4 number of passes, that is 1 even plus 1 odd page is equal to 1 pass of odd even sort algorithm. Okay, so you should know this one. So this example is nothing but the sorting n equal to 8 elements using the odd even transposition sort algorithm, and during each page n equal to 8 elements are compared. You should know that. Okay, so what is time? Okay, so this is the sequential version of odd even bubble sort algorithm we have discussed with example. Okay, so it's odd even transposition, and uh, that is the after n phases of odd even expected, and each phase of page or even page requires theta of n comparison. So you should know the serial complexity of this algorithm, that is the odd even sequential algorithm, that is theta of n square. Okay, so this is odd even transposition algorithm. So its parallel version we will discuss in next lecture. We'll stop here. If you have any query, you can discuss.